November 7th, 1943. Carpic Airfield, KH, France. The fierce headwinds over the English Channel were draining fuel at an alarming rate. Second Lieutenant William E. Roach of the 358th Fighter Squadron, 355th Fighter Group, watched his fuel gauges drop dangerously low as his Pratt Whitney R-2800 engine began sputtering. He faced a dire decision. Ahead, the safety of England was tantalizingly close, but with his fuel situation, it seemed impossibly far. Below him, French fields stretched out, some friendly, many occupied by German forces. One airfield stood out, resembling the Allied bases he knew. Roach made his decision and committed to landing. The massive Republic P-47D Thunderbolt, serial number 4222490, nicknamed Beetle, touched down smoothly on the grass field. Following a ground vehicle to a parking area, Roach shut down his engine, and only then noticed the Balkenkreuz on nearby aircraft. The Germans he had been fighting moments earlier now surrounded his cockpit with rifles drawn. Lieutenant Roach's combat career had ended, but the German Luftwaffe's education was about to begin in unexpected ways. What the Germans discovered, when they inspected Beetle, would profoundly change their understanding of American industrial capability and technological sophistication. The P-47 Thunderbolt wasn't just a fighter aircraft. It was a complete representation of American engineering philosophy, production capability, and material abundance. Over the next 18 months, as German engineers carefully dismantled, tested, and flew captured Thunderbolts, they would confront an uncomfortable truth. Germany had not just fallen behind technologically, they had been competing in a completely different category of industrial warfare. The story of captured P-47s in German hands illustrates how overwhelming material superiority, when correctly applied to military aviation, could render tactical excellence and pilot skill insufficient to alter the course of the war. The Thunderbolt would teach German engineers vital lessons that they could never fully apply. Their country lacked the resources, industrial infrastructure, and time to implement what American factories were producing as standard equipment. The capture of William Roach's P-47 on November 7, 1943, was not the first time the Luftwaffe had encountered the Thunderbolt in combat. German pilots had been battling the massive American fighter since April 1943, when the 4th Fighter Group first escorted B-17 bombers into hostile airspace over occupied Europe. Initial impressions from Luftwaffe combat reports were mixed, with a mix of contempt and confusion. German pilots, used to the nimble Focke-Wulf FW-190 and Messerschmitt Bf-109, found the American fighter excessively large, sluggish at low altitudes, and seemingly designed by engineers who had never considered the needs of aerial combat as understood by the Luftwaffe. Combat reports from German fighter units in the spring and summer of 1943 consistently noted the P-47's poor climb rate, clumsy handling at lower altitudes, and what they saw as American pilots' reluctance to engage in traditional turning dogfights. The initial conclusion among experienced Luftwaffe pilots was that the Thunderbolt was an inferior design that could be easily outmaneuvered at medium altitudes, where most combat took place. This assessment would prove disastrously incomplete. However, other details in the same combat reports hinted at something more troubling, contradicting the narrative of American inferiority. Pilots mentioned how Thunderbolts that chose to disengage from combat could not be caught once they entered a dive. They noted the 8 heavy machine guns firing with devastating effect when American pilots did engage. They described armor protection that seemed impervious to standard 7.92mm rounds, often withstanding even 20mm cannon fire. Most worryingly, they reported that even heavily damaged Thunderbolts managed to fly, limping back to England with battle damage that would have destroyed any German fighter. Damaged P-47s routinely returned to base, missing sections of wings. With oil streaming from engines, control surfaces shot away, yet still under pilot control. When Lieutenant Roach's intact Thunderbolt rolled to a stop at Karpik, the Luftwaffe finally had the chance to carefully examine the aircraft they had been underestimating. Local Luftwaffe personnel quickly recognized the intelligence value of capturing a complete, undamaged example of the American fighter. Within hours, Beetle was surrounded by armed guards to prevent sabotage or damage. American markings were swiftly painted over with German Balkenkreuz insignia, and bright yellow identification paint was applied to the undersurfaces and tail, a standard Luftwaffe practice for captured aircraft, marked with RLM-04 yellow to prevent friendly fire from German anti-aircraft gunners. Soon after, arrangements were made to transfer the aircraft to Rechlin, the Luftwaffe's leading testing facility. Located roughly 100 kilometers northwest of Berlin in Mecklenburg, the aircraft received the designation T9 plus FK, assigned by the Circus Rosarius Evaluation Unit. Hans Werner Lerche, the principal test pilot and chief engineer at Airprobung Stella Rechlin, was tasked with conducting the initial evaluation flights. Lerche, who would ultimately fly over 125 different aircraft types during the war without ever crashing or seriously damaging an aircraft, approached the P-47 with a mix of professional curiosity and appropriate caution, considering the unfamiliar systems of the aircraft. His first impressions, documented in his logbook and later published in his memoirs Luftwaffe Test Pilots Flying Captured Allied Aircraft of World War II, reflected surprise at the complexity of the cockpit. The instrument panel contained what appeared to be twice as many gauges as those found in German fighters. Strange levers controlled systems Lerche had never encountered in German designs. The turbosupercharger system required an understanding of exhaust flow management, a concept that was theoretical in German aviation but standard in American designs. The constant speed propeller operated differently from German equivalents. Most puzzling was the elaborate automatic engine management system, which German pilots handled manually through constant throttle and mixture adjustments. Lerche noted, in his memoirs, the P-47 cockpit could baffle even an experienced pilot. I gradually learned the function of most of the levers and instruments, though some obscure controls were not immediately clear to me. He spent considerable time on the ground experimenting with controls and studying the layout before attempting flight, demonstrating his methodical approach to test flying unfamiliar aircraft without pilots' manuals or operational documentation. The engine start sequence alone revealed a level of sophistication beyond typical German practices. The Pratt Whitney R-2800 double wasp engine required specific procedures to properly initialize the massive turbo-supercharger system. Lerche followed the process carefully, cataloging each step with his engineer's mind, deducing the purpose of each action. When the 18-cylinder radial engine roared to life, it produced a sound unlike the sharp bark of German inline engines or even the BMW 801 radial engine powering the FW190. It was a deep, powerful rumble that spoke of enormous displacement and tremendous power reserves held in check. Lerche taxied cautiously, feeling the weight of the aircraft through the controls. The P-47D weighed nearly 10,000 lbs empty, and this example still carried a substantial fuel and ammunition load, bringing its weight closer to 13,500 lbs. For comparison, the FW190A8, one of Germany's heaviest single-seat fighters, weighed about 7,150 lbs empty and approximately 10,800 lbs at maximum loaded weight. The Thunderbolt was genuinely massive for a single-seat fighter, even larger than some twin-engine aircraft in Luftwaffe service. Lerche advanced the throttle for takeoff, and the difference between German and American engineering philosophies became immediately clear. The R-2800 produced 2,000 horsepower at standard boost, reaching 2,300 horsepower with water methanol injection. The BMW 801D, Germany's finest radial engine, and the power plant of the FW190 produced between 1,700 and 1,730 horsepower at maximum continuous power. Despite this power advantage, the P-47's greater weight meant the takeoff run was longer than Lerche had expected, consuming nearly the entire length of the grass field. However, once airborne, Lerche began to understand why German pilots who had fought Thunderbolts only at low altitudes had fundamentally misjudged the aircraft's abilities. He climbed steadily, nursing the turbosupercharger to operating temperature as altitude increased. Below 15,000 feet, the P-47 felt exactly as German pilots had described: heavy, sluggish in turns, and unable to match German fighters in maneuverability. Its rate of climb was mediocre at best compared to the FW190 or BF109. At this altitude, any competent German pilot in a contemporary fighter could easily outmaneuver the Thunderbolt in sustained turning combat. But above 20,000 feet, the aircraft's characteristics completely transformed. The turbosupercharger, powered by exhaust gases and becoming more efficient as air pressure decreased, began forcing large amounts of compressed air into the engine cylinders. While German engines struggled for oxygen and lost power at higher altitudes, the R-2800 maintained full-rated power. At 25,000 feet, where German fighters were operating at about 70% of their sea-level power, the Thunderbolt's engine still produced full-rated output. Lerche pushed the throttle forward at 25,000 feet, and the Thunderbolt accelerated with surprising vigor for such a large aircraft. He rolled into a dive to test its high-speed characteristics, and the aircraft responded with an enthusiasm that bordered on violent. The P-47 accelerated past 500 mph in the steep dive, reaching speeds where the controls began to feel much more responsive than expected. The controls stiffened dramatically as airflow compressed around the airframe. At this speed, recovering from the dive required both hands on the control stick and considerable physical strength. The aircraft was nearing the limits of compressibility, effects not fully understood until the jet age. The roll rate immediately impressed Lerche, contradicting everything German pilots had assumed about the heavy American fighter. Despite its size and weight, the Thunderbolt could roll faster than any German fighter Lerche had flown, including the FW190, which was renowned for its excellent roll performance. This characteristic, along with its powerful dive speed, gave the Thunderbolt a distinct tactical advantage that German pilots had reported but hadn't fully grasped. An American pilot in trouble at high altitude could simply roll inverted and dive away at speeds no German fighter could match. Any Luftwaffe pilot attempting to pursue would encounter compressibility effects that the P-47's stronger airframe and more responsive controls handled much more effectively. Lerche flew the captured Thunderbolt through a comprehensive test program, exploring the flight envelope systematically according to Rechlin's standard evaluation procedures. His preliminary report contained observations that raised concerns among Luftwaffe headquarters, which still believed German fighter designs were superior. At altitudes above 25,000 feet, where Allied bombers were increasingly flying to avoid German flak, the P-47 Thunderbolt wasn't just on par with German fighters, it surpassed them in crucial areas, negating German advantages in maneuverability and climb rate. Over the following weeks, Rechlin's engineers subjected Beetle to exhaustive testing according to standard protocols. They photographed every component from multiple angles, measured each dimension with precision instruments, and weighed every major part and assembly. They tested every system under various conditions. Special attention was given to the turbo-supercharger system, as it represented the primary difference between American and German high-altitude performance. What they discovered during the detailed examination shocked engineers accustomed to resource-constrained design philosophies. The Pratt Whitney R-2800 double Wasp engine consisted of 18 cylinders, arranged in 2 rows of 9 cylinders around a central crankshaft, with a total displacement of 2,140 cubic inches, or 45.958 liters. In comparison, the BMW 801D displaced 2,560 cubic inches, 41.8 liters. However, displacement alone didn't explain the significant power difference between the engines. The R-2800 incorporated forged aluminum alloy pistons, sodium-cooled exhaust valves to handle extreme temperatures, and a crankshaft forged from high-grade steel alloy that German metallurgists examined with professional envy, recognizing materials they could no longer obtain in sufficient quantities. The quality of American materials and manufacturing precision amazed the German inspection team. Every component showed evidence of precision manufacturing with tight tolerances. Surface finishes were smooth across all parts, and the magnetos used materials that were increasingly scarce in Germany. The spark plugs incorporated high-grade ceramics of superior quality compared to German equivalents. The fuel injection system operated with precision that German engineers typically associated with laboratory equipment, rather than combat aircraft expected to function reliably under harsh conditions. Most telling was the fact that the entire engine showed no signs of material substitution or quality compromises, which had become common in late-war German production due to resource limitations. The turbo-supercharger system revealed engineering sophistication that Germany had tried to develop but never successfully implemented in production aircraft. Exhaust gases from all 18 cylinders were collected through manifolds and routed through insulated pipes along each side of the fuselage to a turbine unit located behind and below the cockpit. This turbine, spinning at tremendous speed and driven by hot exhaust gases, powered a centrifugal compressor that forced additional air into the engine's supercharger. The system included an intercooler to reduce the temperature of the compressed air, increasing its density and preventing destructive detonation. Automatic regulators controlled boost pressure and turbine speed, requiring little pilot intervention beyond setting the desired manifold pressure. German engineers understood the theoretical principles perfectly and had conducted experimental programs to explore similar approaches. But implementing such a system in mass-produced combat aircraft proved impossible. For Germany, due to material shortages and manufacturing limitations by 1943, the turbo-supercharger required exotic high-temperature alloys for turbine blades that had to withstand extreme conditions while spinning at high speeds. The control system demanded precision manufacturing and reliable components. The extensive ducting needed heat-resistant materials and perfect seals to function efficiently. Every element of the system had to work reliably in combat, exposed to vibration, temperature extremes ranging from 60 degrees to soaring heat, all of which made it a complex challenge for German industry to replicate. At altitude, temperatures could soar above 200 degrees near the engine, compounded by potential battle damage. The Americans had addressed all these challenges and integrated the entire system as standard on every P-47 produced. The turbo-supercharger was not experimental or reserved for special missions, but was part of regular production, installed in thousands of aircraft. This casual implementation of advanced technology in standard production aircraft revealed an industrial capacity that German engineers struggled to fully grasp. German technical reports from the Rechlin evaluation noted that the turbo-supercharger alone demonstrated a level of engineering sophistication and manufacturing capability that exceeded German capacity to replicate in mass production. The materials, precision manufacturing, and quality control required to produce such systems reliably, at scale, surpassed what German industry could manage in 1943 due to strategic material shortages and the degrading manufacturing standards caused by Allied bombing and the replacement of skilled workers with forced labor. The armament installation was another example of American abundance and attention to detail. The P-47D was equipped with 8 Browning M2 50 caliber machine guns, 4 mounted in each wing. Most German fighters of the time carried a mix of typically 4 machine guns and 2 20mm cannons, or in early models, 6 machine guns in total. The American decision to install 8 heavy machine guns was a deliberate move to maximize firepower, even at the cost of added weight and complexity. Each machine gun was fed from a separate ammunition box built into the wing structure, each box holding 425 rounds, giving a total ammunition capacity of 3,400 rounds across all 8 guns. For comparison, the FW-190A typically carried about 2,000 rounds for its machine guns and 500 rounds for its cannons. The P-47 pilot could fire all 8 guns continuously for around 20 seconds before depleting the ammunition, with a combined rate of fire of nearly 100 rounds per second. When all 8 guns were properly harmonized to converge at a single point, the volume of fire was overwhelming for any target. German test firings of the captured aircraft's armament system confirmed its devastating impact. The quality of the installation impressed German armament specialists. Each gun was mounted in an electrically heated bay to prevent freezing at high altitudes where temperatures could drop to 60°C or lower. Spent cartridge cases and disintegrating belt links were collected through chutes and ejected through ports in the wing's lower surface, ensuring they did not damage the aircraft or interfere with the control surfaces. The system functioned flawlessly during testing, firing thousands of rounds under various atmospheric conditions with no jamming or feeding issues. The quality of the ammunition also showcased American industrial strength. The 50 caliber rounds were manufactured to consistent specifications with armor-piercing cores, reliable incendiary compounds, and predictable tracer elements. Testing revealed that American ammunition was more reliable than its German counterparts, which had suffered quality degradation as strategic materials became scarce. The P-47's armor protection demonstrated the American focus on pilot survivability, even at the expense of significant weight. The cockpit was surrounded by heavy armor plating on multiple sides, with the pilot sitting in what American designers called an armored bathtub, providing protection from below and behind. The windscreen was made of thick, bulletproof glass capable of stopping machine gun rounds and withstanding cannon shell fragments. Additional armor plates shielded critical systems, including the oil coolers and vulnerable turbosupercharger. The total armor weight exceeded 200 lbs, about the same as adding 2 more machine guns with ammunition. German fighters typically carried less comprehensive armor, prioritizing lighter weight and performance, while accepting higher pilot casualties as an inevitable part of combat. This design philosophy difference was also evident in maintenance accessibility. American designers clearly anticipated that mechanics at forward air bases would need to service aircraft quickly, possibly under adverse conditions or enemy attack. Every major component could be accessed through large panels secured with quick-release fasteners, requiring only simple tools. The massive engine could be swapped out in the field within a few hours using standard hoisting equipment and following clearly documented procedures. German fighters, designed for factory-level maintenance of major repairs, often required more extensive disassembly to service major components. This difference highlighted American abundance versus German scarcity. The Americans could afford to dedicate engineering resources to maintainability, as their industrial capacity allowed them to optimize designs for operational efficiency rather than simply focusing on production efficiency. The radio installation in the captured P-47 was another area where American technology outperformed German equivalents. The aircraft was equipped with an SCR-274N command radio for air-to-air and air-to-ground communication, as well as an SCR-515A liaison radio providing additional communication channels. Both units offered clarity and range that surpassed contemporary German radio systems. German radios frequently suffered from interference issues that American engineers had apparently solved with superior component design and better shielding. Additionally, the radios were integrated with an identification friend or foe (IFF) system, automatically identifying friendly aircraft to ground controllers and preventing friendly fire incidents. This level of automated identification was a sophistication German forces lacked in 1943. Perhaps the most significant revelation for German engineers came not from any one advanced system, but from the overall impression of quality and completeness across the entire aircraft. Every component appeared to be the best possible version that American engineers could design and manufacturers could produce. Nothing was obviously compromised due to material shortages, and no substitute materials were used because the preferred materials were unavailable. There were no signs of the desperate improvisations that increasingly marked late-war German production, as strategic bombing devastated industrial capacity and material shortages became severe. German technical reports compiled at Rechlin and distributed through Luftwaffe technical services emphasized this point repeatedly. The P-47 Thunderbolt had been built exactly as the designers intended, using all specified materials and processes, with no apparent compromises forced by resource constraints. This level of manufacturing fidelity to original design specifications was becoming increasingly difficult for German industry to replicate as the war progressed. The flight testing program continued through the winter of 1943 and into early 1944, as more P-47s were captured and brought to Rechlin for comparative evaluation. On May 29, 1944, another P-47 landed in German hands when Second Lieutenant Lloyd S. Hathcock of the 3001st Fighter Squadron, 302nd Fighter Group, became disoriented during a ferry flight and mistakenly landed at the enemy-held Rome Littorio airfield in Italy. His aircraft, serial number 4275971, was quickly seized by German forces. This P-47 had previously been the personal aircraft of George Nowotny, an 8 Victory Ace with the 317th Fighter Squadron. The Germans transferred the aircraft to Rechlin, where it was initially designated 8+6, then later moved to Circus Rosarius on October 12, 1944. Where it was given the designation T9+LK. The testing data accumulated at Rechlin led to tactical recommendations that were distributed to frontline Luftwaffe fighter units. These recommendations advised engaging P-47s below 15,000 feet, where the Thunderbolt's poor low-altitude performance and slow rate of climb gave German fighters a clear advantage in that range. Pilots were specifically cautioned to avoid diving away from attacking Thunderbolts, as the American fighter would simply accelerate to speeds German aircraft could not match in a dive. The reports also noted that damaged P-47s frequently continued flying despite battle damage that would have destroyed German fighters, meaning attacks needed to be pressed aggressively with concentrated fire rather than relying on a few hits to bring the aircraft down. However, the tactical advice, while useful to individual pilots, could not address the larger strategic problem that was becoming increasingly clear. Germany was fighting an opponent with effectively unlimited material resources compared to its own industrial capacity. Every damaged or destroyed P-47 could be replaced within days from production that exceeded 300 aircraft per month at peak output. American pilot training programs produced skilled aviators in numbers that Germany could no longer match, as training was compressed and fuel shortages limited flight hours. The logistics system supporting American Thunderbolt operations delivered fuel, ammunition, and spare parts without constraint, while German logistics were undermined by relentless Allied air attacks. The captured P-47s were eventually transferred to Circus Rosarius, the special Luftwaffe demonstration unit commanded by Flugkapitän Theodor Rosarius. This specialized unit traveled to frontline fighter bases across occupied Europe, allowing German pilots to see captured Allied aircraft firsthand and learn their recognition features and combat characteristics. These demonstrations served a dual purpose, educational and psychological. Pilots learned to recognize enemy aircraft and understand their tactical features. But they also saw physical evidence that Allied equipment often outclassed their own in specific key capabilities, particularly at the high altitudes where combat increasingly took place. As the war progressed, interviews with Luftwaffe pilots who attended the Circus Rosarius demonstrations revealed the psychological impact of seeing the captured American fighters' capabilities showcased directly. While Circus Rosarius pilots could demonstrate that German fighters maintained advantages in certain flight regimes, particularly at medium altitudes, the demonstrations clearly illustrated that at the altitudes where American bomber formations operated, escorted by P-47s and later P-51s, German fighters were at a distinct disadvantage. The intelligence gathered from captured P-47s provided detailed performance data that contradicted some of the optimistic assumptions circulating in Luftwaffe briefings earlier in the war. At sea level, the P-47D reached a maximum speed of about 350 meters, not particularly impressive compared to the FW-119A's 408 mph at the same altitude. At 10,000 feet, the Thunderbolt hit approximately 375 mph. However, at 30,000 feet, the P-47 reached 426 mph, while the Focke-Wulf struggled to reach 370 mph, and the Bf-109G managed around 385 mph. The performance advantage at combat altitudes was clear and growing more significant as Allied bombers flew higher to evade German anti-aircraft fire. The service ceiling comparison was equally discouraging for German pilots. The P-47 Thunderbolt service ceiling reached 42,000 feet, while German fighters rarely operated effectively above 35,000 feet, and their performance rapidly degraded at higher altitudes due to reduced engine power in the thin air. American bomber formations could operate at altitudes where German interceptors could barely reach them, and those that did lacked the power reserves for effective combat maneuvers. P-47 escorts operated comfortably at these altitudes, maintaining full combat capability, while German fighters struggled. Range comparisons between American and German fighters revealed another aspect of American industrial and logistical superiority. With external fuel tanks, the P-47D could escort bombers on missions deep into Germany. Early P-47 models had limited range, which restricted their effectiveness, but by 1944, Thunderbolts equipped with 108-gallon drop tanks routinely flew missions covering over 1,000 miles. German fighters, primarily designed for short-range interception missions to defend the Reich, lacked the internal fuel capacity for extended operations. This difference in operational radius meant that American fighters could engage at times and places of their choosing, while German fighters were forced into defensive roles. The captured Thunderbolts also offered insights into American pilot training and tactical doctrine through analysis of gun camera footage and combat damage patterns on aircraft that had survived combat before being captured. The evidence suggested that American pilots consistently employed tactics that leveraged the P-47's strengths while avoiding situations that exposed its weaknesses. They maintained high altitudes where the turbosupercharger gave a clear advantage and used dive and zoom attacks instead of sustained turning dogfights, where German fighters had the upper hand. They worked in coordinated pairs or four-ship flights, providing mutual support and rarely engaging in individual combat unless tactically advantageous. The discipline shown in American tactical execution impressed Luftwaffe analysts. Many Luftwaffe pilots, especially experienced aces, preferred to fight solo, relying on personal skill and aggressive tactics to achieve victory. American pilots, however, consistently adhered to established doctrine, supporting each other systematically and rarely allowing personal pride or aggression to override tactical sense. This disciplined approach, combined with superior high-altitude equipment and a growing numerical advantage, created a combination that even veteran German pilots found increasingly difficult to overcome as the war went on. By D-Day in June 1944, the strategic situation had deteriorated to the point where intelligence on captured aircraft offered little practical value to Germany's war effort. The Luftwaffe understood that American equipment was superior in key areas. They grasped American tactics and had detailed technical data on Allied aircraft performance. But this knowledge couldn't produce the resources, strategic materials, manufacturing capacity, and trained personnel needed to effectively compete. The Rechlin reports, carefully compiled and professionally distributed throughout the Luftwaffe technical services, primarily served to document the technological and industrial gap driving Germany toward inevitable defeat. The comparison between American and German engine production illustrated the impossible position Germany faced. By the end of the war, Pratt Whitney, alongside Leon C. Ford Motor Company, produced over 125,000 V-2800 engines. This single-engine type's production exceeded Germany's entire combat aircraft engine production, with BMW producing about 61,000 examples of the 801 radial engine throughout the entire war. The Daimler-Benz DB605, Germany's most produced inline engine, reached approximately 42,400 units in total production. However, American production of just one advanced engine type surpassed Germany's entire output of all combat aircraft engines combined. In 1944, American industry produced roughly 96,000 aircraft, while Germany produced about 25,000 of all types. The United States alone produced 38,000 fighters, 16,000 heavy bombers, plus thousands of medium bombers, transports, and trainers. When combined with British and Soviet production, the Allied advantage in aircraft production exceeded a 5.1 ratio by 1944. The industrial base supporting this production operated on a scale that Germany could not match. The Aluminum Company of America alone produced more aluminum than Germany's entire aluminum industry. Individual American steel plants often outproduced the entire Ruhr industrial region. American automotive factories operated on moving assembly lines, while German plants used batch production methods. Even the machine tools that built aircraft were produced in quantities that allowed American industry to supply not only its own needs but also substantial quantities to British and Soviet allies. The captured P-47s ultimately ended their service in the chaotic final months of the European War. The aircraft designated T-9+FK, originally William Roach's Beetle, was recovered by American forces at Göttingen in May 1945. Found among a collection of captured Allied aircraft the Germans had been evaluating. Photographs taken by American forces show the aircraft still bearing partial German markings, parked alongside FW-190s and BF-109s in what was essentially a museum of captured equipment, documenting the Luftwaffe's intelligence-gathering efforts. The Thunderbolts that served with German evaluation units provided German pilots and engineers with an education they desperately needed, but received too late to matter strategically. These aircraft demonstrated that American industrial philosophy prioritized absolute capability over efficient elegance, abundant resources over careful optimization, and systematic material advantage over individual technical excellence. When implemented with nearly unlimited resources and manufacturing capacity, these priorities produced weapon systems that outclassed their German equivalents in the aggregate, even when German designs showed superior characteristics in isolated parameters. The lesson extended far beyond the P-47 itself. Every category of captured American equipment told the same fundamental story. The B-17 Flying Fortress, with its quartet of turbo-supercharged Wright Cyclone engines, represented a strategic bombing capability that Germany never achieved. The P-51 Mustang, combining American airframe engineering with the British Rolls-Royce Merlin engine, created what many historians consider the finest piston-engine fighter of the war. The P-38 Lightning, with its twin turbo-supercharged engines and tricycle landing gear, demonstrated America's willingness to pursue unconventional solutions. Each aircraft type revealed the same fundamental American approach: solve problems through superior engineering supported by unlimited industrial capacity, rather than through clever optimization constrained by resource scarcity. Luftwaffe analysts clearly observed that they were not being defeated by superior tactics or better-trained pilots, though American training programs were producing adequate pilots in overwhelming numbers. They were being defeated by an industrial system that could design adequate equipment and then produce it in quantities that rendered German qualitative advantages increasingly irrelevant. The Americans designed to their industrial strengths, leveraging massive manufacturing capacity, abundant raw materials, and efficient logistics. By 1943, Germany was designing despite crippling industrial limitations, attempting to achieve through engineering ingenuity what it could no longer accomplish through industrial might. The strategic implications were well documented throughout the Luftwaffe's technical services. By the end of 1943, Germany had entered the war with arguably the world's most advanced air force, equipped with aircraft generally superior to their opponents on a 1-1 basis. German pilots were better trained than most of their opponents initially, and their tactics were more refined. But German industry lacked the capacity to sustain these advantages against opponents with far greater industrial resources. American aircraft production doubled repeatedly in 1940, again in 1941, again in 1942, and continued expanding until by 1944, American factories were producing over 96,000 aircraft annually, while Germany never exceeded 40,000 aircraft in any given year, despite desperate efforts to increase production. The quality gap between American and German aircraft steadily widened. In 1942, German aircraft were often superior to their American counterparts. By 1944, American aircraft had matched or surpassed German designs in virtually every important category. By 1945, the gap had become a chasm. American fighters like the P-51H and P-47N represented evolutionary refinements of already excellent basic designs. German fighters like the TA-152 represented desperate efforts to extract more performance from industrial systems that were collapsing under the weight of strategic bombing, raw material shortages, and the replacement of skilled workers with poorly trained forced labor. The psychological toll on Luftwaffe morale, facing an endless stream of capable enemy aircraft, proved as devastating as the material losses. German pilots reported feeling less like warriors in honorable combat and more like targets in a systematic destruction campaign. No matter how many Allied aircraft they shot down, more appeared the next day. No matter how skillfully they fought, American numerical superiority eventually prevailed through sheer attrition. The awareness that their opponent's equipment was often superior, delivered in far greater quantities, supported by better logistics, and flown by adequately trained pilots who were quickly replaced when lost, created a pervasive sense of inevitable defeat that spread throughout the fighter forces in 1944. The captured P-47s served as tangible evidence of this harsh reality. These were not exaggerated intelligence reports or propaganda claims. They were actual aircraft that German pilots could examine firsthand. The Thunderbolt was not a miracle weapon or a revolutionary technological breakthrough. It was simply an excellent fighter aircraft, well designed for its mission, adequately powered, well-armed, appropriately protected, and produced in sufficient quantities to overwhelm opposition through the systematic application of material superiority. The final historical irony was that the Germans learned these lessons thoroughly, documented them meticulously, and fully understood the implications, yet could never apply the knowledge they gained. Understanding American industrial superiority did not give Germany the aluminum, steel, fuel, skilled labor, undamaged factories, or functioning transportation networks necessary to produce equivalent aircraft in equivalent quantities. Knowing the P-47's exact capabilities did not provide the high-temperature alloys, precision manufacturing equipment, quality control systems, or trained workforce needed to build comparable turbo-supercharger systems. The intelligence gathered from captured aircraft documented the dimensions of Germany's defeat with professional thoroughness, but offered no realistic solution to avoid that defeat. When Allied forces captured Rechlin and its associated facilities in May 1945, they found extensive documentation of the captured aircraft evaluation program. German technical reports filled filing cabinets, detailing every measurable characteristic of every American and British aircraft examined during the war. The reports were models of technical thoroughness and scientific objectivity. They also represented thousands of man-hours spent meticulously documenting capabilities that Germany could observe and measure, but could never replicate due to their deteriorating industrial situation. American technical intelligence. Teams who reviewed the German reports after the war noted with professional interest that German engineers had understood American aircraft capabilities in greater detail than American commanders sometimes did. The Germans had identified weaknesses in American designs that American pilots learned to work around through experience. The technical analysis was often more detailed and rigorous than comparable American evaluations of their own equipment. German engineering competence had never been in question. However, the American reviewers also noted what the German reports implicitly revealed about Germany's strategic situation. Germany had attempted to fight a modern industrial war with an industrial base insufficient for the task. They compensated through excellent engineering, superior pilot training in the early years of the war, and tactical innovation born of necessity. These advantages had sustained them through early victories against opponents with similar resource constraints. But against an opponent like the United States, with an industrial capacity exceeding all other major powers combined, excellent engineering and tactical skill could only delay the inevitable outcome, not alter it. The story of German engineers examining captured P-47 Thunderbolts offers a clear case study in the realities of industrial warfare as it had evolved by the Second World War. The Thunderbolt succeeded, not because it was the absolute best fighter aircraft, by every conceivable measure, but because it was a highly effective fighter aircraft produced in such large quantities that isolated examples of technical superiority became strategically irrelevant. American industry built 15,783 Thunderbolts, while simultaneously producing 15,486 P-51 Mustangs, 10,037 P-38 Lightnings, 13,738 F-6F Hellcats, and 12,571 F-4U Corsairs. Total American fighter production exceeded 70,000 aircraft during the war. Each of these aircraft represented thousands of hours of skilled labor, tons of aluminum and steel, and hundreds of precision components, manufacturing capacity that Germany simply could not match. The P-47 Thunderbolt became a symbol of American industrial dominance to the Germans. Pilots who fought against the P-47 Thunderbolt often referred to it by the same nickname American pilots had coined, calling it the Jug in recognition of its ungainly appearance. They also called it Indiana, after the Thunderbird emblem many squadrons painted on the engine cowling. As losses mounted and the strategic situation worsened, some Luftwaffe pilots simply referred to it as that 8-gun fighter and learned through bitter experience to avoid engaging Thunderbolts at altitudes where the American fighter held a distinct tactical advantage. This increasingly meant avoiding combat above 20,000 feet, where the P-47's turbosupercharger gave it decisive performance superiority. By the war's end, P-47 Thunderbolts had destroyed around 3,752 enemy aircraft in aerial combat, while approximately 499 P-47s were lost to all causes, including operational accidents, mechanical failures, and ground attack missions. This roughly 1.1 exchange rate in total losses might seem unremarkable, until considering that the Thunderbolt served primarily in the ground attack role from mid-1944 onward, facing intense anti-aircraft fire during low-level missions rather than engaging primarily in air-to-air combat. In the pure fighter escort role during 1943 and early 1944, P-47s achieved much better exchange rates, particularly at high altitudes, where the turbo-supercharger advantage was most pronounced. The ground attack role revealed another dimension of American design philosophy, emphasizing versatility. When P-51 Mustangs, with their superior range, began taking over bomber escort duties in 1944, the 9th Air Force reassigned many Thunderbolt groups to tactical air support missions. The rugged P-47, with its reliable air-cooled radial engine and heavy armor protection, proved exceptionally well suited for dangerous low-altitude attack missions. The same characteristics that made it seem ponderous in low-altitude dogfights: substantial size, heavy weight, comprehensive armor, and powerful armament, made it nearly ideal for ground attack missions, where survivability and firepower mattered more than maneuverability. Thunderbolt pilots flying ground attack missions destroyed staggering quantities of German military equipment. Official claims, documented through gun camera footage and after-action reports, included over 86,000 railway cars, 9,000 locomotives, 6,000 armored fighting vehicles, and 68,000 trucks destroyed or damaged. While such claims inevitably included some duplication, the scale of destruction was undeniable and had a measurable impact on German military operations. The P-47, armed with bombs and rockets in addition to its 8 machine guns, had evolved into a true multi-role combat aircraft. German ground forces learned to recognize and fear the characteristic sound of the Pratt Whitney R-2800 radial engines at low altitude. The deep rumble provided a warning of impending attacks that German troops were largely helpless to prevent. The psychological impact of constant air attacks, combined with substantial material losses and the disruption of logistics and communications, measurably degraded the combat effectiveness of German ground forces throughout 1944 and 1945. The fates of the specific captured aircraft provide an interesting epilogue to this story. William Roach's P-47D, Beetle 42-22492, designated T9 plus FK by the Germans, survived the war and was recovered by American forces at Göttingen in May 1945. After evaluation by American intelligence teams who examined German testing procedures, the aircraft was eventually scrapped. Lloyd Hathcock's P-47D 4275971, designated T9 plus LK, met a similar fate. It was recovered but not preserved for historical purposes. The pilot's fates after capture differed significantly. William Roach spent the remainder of the war at Stalag Luftwaffe in Bath, Germany. He was liberated by Soviet forces in May 1945 and returned to the United States. Lloyd Hathcock spent 11 months as a prisoner of war, primarily at Stalag Luftwaffe, the site of the famous Great Escape that had occurred just 3 months before his arrival. He was the only African-American pilot among thousands of white prisoners at the camp. When Soviet forces advanced westward in January 1945, German forces evacuated the camp, forcing prisoners on a brutal winter march to Stalag 7A and then Stalag 13D. He was liberated by Allied forces in April 1945. Hathcock returned to the United States, where he played a significant role in the post-war desegregation of the U.S. Air Force. He later pioneered innovations in aerial reconnaissance photography at Wright-Patterson Air Force Base. Hans Werner Lerche, who survived the war despite flying 125 different aircraft types, including numerous captured Allied aircraft, holds a remarkable safety record, never crashing or seriously damaging a single aircraft throughout his test pilot career. After the war, he provided extensive debriefings to Allied intelligence services about German aircraft development programs. His memoirs, published in 1977 in German and translated into English in 1980, provide one of the most detailed, first-hand accounts of the German captured aircraft evaluation program and offer valuable insights into how the Luftwaffe assessed and understood American technology. The broader lesson emerging from the story of captured P-47 Thunderbolts in German hands transcends the specific technical details of a single aircraft. The Thunderbolt evaluation at Rechlin revealed that by 1943, the outcome of the air war over Europe was not being determined by pilot skill, tactical innovation, or even aircraft performance in narrow technical terms, but by industrial capacity applied on a national scale. The nation that could design adequate equipment and produce it in overwhelming quantities, while simultaneously producing everything else a modern military requires, would inevitably defeat opponents who produced technically superior equipment in insufficient quantities. By late 1943, Germany found itself in the position of trying to compete industrially against opponents whose combined industrial capacity exceeded its own by factors of 5 or more. When Britain refused to surrender after France fell, when the Soviet Union survived the initial German onslaught and moved its industry beyond German reach, and when the United States entered the war with its vast, untouched industrial base, Germany's path to military victory effectively closed. The only remaining question was how long Germany could continue fighting and how much destruction would occur before the inevitable conclusion. The story of Beetle and the other captured Thunderbolts at Rechlin thus becomes a microcosm of Germany's broader strategic dilemma. German engineers could examine American equipment, understand American capabilities, and accurately assess American industrial strength. This knowledge was gathered professionally, carefully analyzed, and thoroughly documented. But knowledge alone could not produce the aluminum, steel, rubber fuel, machine tools, skilled workers, undamaged factories, and functioning railroads required to compete with American industrial output. The Republic P-47 Thunderbolt, examined in minute detail by German engineers at Rechlin, revealed a final truth about industrialized warfare in the 20th century. Material abundance, systematically applied through competent engineering and adequate tactical execution, would defeat technical excellence constrained by resource scarcity. The most powerful element in America's arsenal was not any individual technology, however impressive, but rather the complete industrial system that could conceive, design, develop, test, produce, and logistically support thousands of complex weapon systems simultaneously, while maintaining quality and continuously improving designs based on combat experience. The captured Thunderbolts taught this lesson with undeniable clarity. German engineers measured it precisely, documented it professionally, and reported it accurately through their chain of command. However, the lesson arrived too late to make a difference. By the time William Roach's Beetle was being meticulously examined at Rechlin in late 1943, the outcome of the war had already been determined by industrial mathematics, factors that no amount of German engineering skill or pilot courage could overcome. The Thunderbolts sitting on German airfields, now bearing hastily applied Balkenkreuz markings over American stars, symbolized a future that had already arrived, one in which industrial capacity had become the decisive factor in modern warfare.